Okay. So what we have done so far is we had a very high level introduction of computing systems. And then how does a program work, really? Like starting what we call the journey of the computer, uh, source code, compiling, the assembling, machine code, loading this to the memory. The CPU will fetch instructions from the memory, execute them one instruction at a time, and then you produce the output, you display it on the screen, or you send it to the output, whatever format you want your output to be, right? And this is mostly what would happen with every single program. And then we jumped from there into, okay, now I have programs, I have machines. I want to decide, or I want to know how do I decide whether a machine is good or bad, and what is even the definition of good or bad, or better than another one. And we raised this concept of computing system performance or computer architecture performance. And then we said quantitatively measuring the performance of computing machines is in fact very key. It's the backbone of modern computer architecture from early 80s up until now, right? So every single architecture paper, you will have an evaluation section that does uses one of the equations we have had last time, either the iron roll or Amdahl's law, or a combination of them using geometric mean or harmonic mean or the normal mean. And in industry, the same thing. Our story of an architect, again, sitting down, drinking the coffee, coming up with an idea. You need to convince others with this idea. How do I convince them? Well, you should speak the language that everyone is speaking. So previously we were achieving performance X, now we're achieving 1.2X, so are 20% better, right? And then people will start listening to you for that proposal. So you must have a quantitative way of really saying that you are proposing something better, or why there is a trade-off between two things and which one you choose. Good. And this was that topic for the last lecture. And I guess the last thing we have done was trying to fill in this table for every single term in the equation of the iron rule of performance. What is the impact, looking into the full computing stack? What is the impact of each one? Last time we had this discussion briefly, so now we want to simply, well, emphasize it, spotlight on it, on having it in a table format, right? And again, you will see from the discussion that some of these metrics are vague, right? Like they are not, there are trade-offs. You can look into it from one angle that it has an impact, from another angle that it does not have an impact. So it's a worth having discussion. Good. But don't take this as, again, math, a rule, a table that you have to memorize. It's not the case, right? Just building the intuition of why a certain layer in the stack would impact a certain term in that performance equation. Good. So in our equation, we had three terms. We had the instruction count, we had the CPI, and we had the clock cycle, or the frequency, or the clock period, right? And we said, well, multiplying these three gives you the total execution time of a program in a certain machine, right? Now, this program on its own, if you remember our introduction lecture, lecture 0, we said, well, before even having a high-level language, before even having 2SH, you would be devising an algorithm. You would be write an algorithm that has a certain order of execution or does an operation in a certain way, and you had the big O notation in 2SI. So now, how does this algorithm, aside from which language I use to implement it, would impact instruction count, if it would impact CPI and clock cycle? What do you think? Would the algorithm, for example, impact the instruction count? Clearly, yes, right? We said last time instruction count is directly impacted by the software layer mainly, right? Because this is how the compiler will generate the program, and your program is in fact a function of the algorithmic device. What about CPI? Cycles per instruction. Yeah, here it starts becoming interesting a little bit. Yes or no? What do you think? So think about the following. When we say cycle per instruction, we are not even looking into the relationship among instructions. We're looking into a fine-grained layer, which is only a single instruction. If I have that instruction, how much time does it take to execute, right? Because CPI is simply a latency measure, right? Cycles. Does this depend on the algorithm? How? Great. An excellent point. So you are saying if I'm writing an optimized, and this is why we're having this discussion. So if I'm writing an optimized code, well, I'm coming up with an optimized algorithm. For example, instead of, remember your algorithmic kind of discussions, instead of going with, well, n squared to n log n on this type of discussion for sorting, searching, and these algorithms, right? Now I'm reducing simply the, well, it's asymptotic, but let's say simply we're reducing the total time that a program takes, right? True. But the total time a program takes is the full equation. Right now, we're trying to distill it into one term at a time. So if I optimize my algorithm, I might be simply getting rid of some instructions and keeping some, reordering them in a certain way, right? But at the end of the day, you are impacting the coarse grain of the program. But taking one instruction out of this, are you able to control from the algorithm side? Not much, right? So it's true that anyone in the rows of this table would impact the total execution time, right? There is no doubt about this. What we're trying to find out is each term impacts which term in the execution time. And this is important to understand because you will start making trade-offs, right? Well, I will optimize here, but I know beforehand that I will never be able to touch, for example, the clock frequency, right? There's nothing I can do about it, right? CPI is mainly a function of, like as a coarse-grained fashion, like just give you very high-level rules. Instruction count is mostly impacted by software, right? Because here I'm talking coarse-grained. The application itself, how many total instructions it has, right? And also compiler, definitely, because we said there is many to one mapping, so the compiler will be able to generate that assembly code accordingly. CPI and clock cycle, on the other hand, are mainly impacted by hardware, right? Because think about the frequency of the machine. Well, running the machine at a certain frequency has nothing to do with what application you are running on top of it, right? And this is why it's a spec in the data sheet of whatever machine you buy, right? You say it runs at 3.2, 3.5, 5 gigs. CPI is where the most of the interesting discussion is because it's somewhere in between, but it's also mostly impacted by hardware because I'm talking about cycles per instruction. So I'm picking up one instruction, right? And I'm trying to say how much time do I take to really execute it, right? Good. So this is at the coarse-grained way. But distilling the software and the hardware, maybe it's also, we go to the next step and say, here in this table, what is the software and what is the hardware? Where should I put the line? Like if I have all these algorithms, programming languages, compilers, ISA, organization, technology, where should I have the line in the sand to separate the two worlds, software and hardware? Yeah. Yeah, that's very good suggestion. Should we become closer? Yeah. The ISA. So ISA, we said before, that's the contract between the two worlds, right? So ISA, it's very hard to consider as a hardware, and it's very hard to consider as a software. It's our border between the hardware and the software. So the line would be, in fact, the ISA row itself. Good? Great. So here we have the software wallet, and here we have the hardware. Or in other words, you can say here is the software, here is the hardware, and here is the software hardware co-design. Good? Great. So we would expect from this discussion that instruction count would be impacted mainly by those software ones, right? So algorithms would impact instruction count. What about programming languages? Would it impact instruction count? What do you think? Yeah. It might. True. So based on the programming language I'm writing my algorithm on, I would end up compiling in a certain way, ending up with a certain number of instructions. For example, if you take a combined language like C or C++ versus taking an interpreted language like Python or Perl or MATLAB or any interpreted language, you will end up with a completely different number of instructions. Combined languages are simply very optimized for runtime. And this is why usually they have this number of assembly instructions at the end. Interpreted languages, there's a lot of interesting discussions in the software community, whether you should even talk about interpreted languages as languages or not, right? But that's a separate topic. But at the end, they are not optimized for runtime. They're optimized for usability. This is why they are usually higher level. Like Python is higher level than C and C++, right? Because it facilitates programming, but it's not very optimized for runtime. There is a very interesting paper, and I believe the code is in GitHub, that they take a very simple sorting algorithm, I believe, they run in C, and then they take the same code and run in Python, and they have 100x difference in performance, right? C is 100x faster than Python for this very simple program, right? So going back to how does this really impact our discussion, where some of these optimizations are coming from, well, the number of instructions you create, right? So programming languages definitely impact the instruction count. What about compiler? That's an easy discussion because we already answered before. We said in last week lecture that from the high-level languages, like if I have a code in C, C++, and then I want to transfer to assembly, even for one ISA, right? So I'm talking about, for example, generating an x86 code. This mapping, is it one-to-one or many-to-one? One-to-one means for every single program, you end up with only one correct version of an assembly code. Many-to-one means for the same high-level C program, you can end up with multiple, all of them are achieving the same functionality, multiple versions of the assembly code. Is it one-to-one or many-to-one? Sorry, one-to-many. So one-to-one or one-to-many? One-to-many, right? Because based on how much optimizations you do in the compiler, and we gave this example in last week, like in GCC, for example, there are multiple compilation options if you are using your command line or even in an IDE that you can say, I want to optimize the code. And there are multiple compiler optimizations like loop unrolling and well, out of order execution and many things, right? So optimized code by the compiler is different than non-optimized code. So this is many-to-one. Sorry, one-to-many. I keep saying it wrong. So one-to-many. So if it's one-to-many, that means the compiler, in fact, impacts how many instructions I create at the assembly level, which is the instruction count, right? So also, I have a term here, right? Good? Are we good so far? Okay. I'm taking my time in this table. I'm okay. I guess last year I spent like maybe almost the whole lecture discussing that table, but that's totally fine because this is key. This is a cornerstone. There are a few cornerstones in architecture. If you got them, you got the intuition. This is one of them, right? And you will see in lab one also you do a lot of these comparisons between, well, instruction types and evaluated performance. We don't cover much of, well, you also see this for different applications, which will show you the software impact, right? You run different benchmarks and you see, well, how do they impact the overall execution time. Now we go to the hardware layer. So let's take one column at a time. For the ISA, does it impact instruction count? And we answered this before, right? What do you think? Yes. And why that's the case? Can you give me an example that we had last lecture? Yeah. Yeah. For one instruction. Exactly. Thank you. And I guess that the clear example we had last time is the swap C function that we said in Intel x86 you can have a single instruction because there is a swap instruction there. But in MEPS, you might end up with 10 or more instructions, right? So the ISA gives you the capability. It tells you what the hardware is able to execute. It defines even, as Steven said, what is a single instruction doing, right? So it's clearly like impacting the total instruction count. Processor organization. So now we're going lower to the hardware. What do you think? Think about it. What do we mean by processor organization, right? Again, we defined this in lecture 0, where we said after the ISA, you have simply the data path and the control path, the ALUs, right? The decode unit. We call this processor organization, right? So that's simply the functional units and how do they connect together that you have in your hardware, right? Which is mainly where we are focusing on that course, organization and architecture. Does this impact instruction count? Any clear answer and argument? Yeah, Arjun. Okay, and the reason is?
As have multiple different processors, they would file and create a number of different
organizations. That's a very good argument. Is there any counter argument? Yeah. That's also a good point. So one example for this is if you have a processor that would have floating point instructions versus non-floating point instructions, then you say, well, if you have floating point support, I mean, like is able to execute floating point hardware, you enable the compiler to create floating point instructions that are executed in hardware, and then you only create that instruction. But then Arjun side can come and say, but this is defined by the ISA, right? Because if you have a floating point instruction versus not, well, yes, you might have the capability in hardware, you don't have it, but at the end of the day, there is a floating point instruction at the hardware that tells the compiler you can create it there, right? See what I mean? So here it starts becoming a little bit vague. So I will leave that. I will come into it later on, right? Any cell that we don't have a very clear answer for, I will put this question mark and we'll discuss it then. Let's first flush whatever is clear, right? So if there is an argument and a counter argument, I guess I will leave it open and we'll come into it later. Technology. What do I mean by technology? Technology is simply the underlying physics, the VLSI technology that you are using. You hear this kind of they call chip war, and then going to 7 nanometers versus 9 versus 12 nanometers. Like previously, every couple of years, we had what we call Moore's law, where we're able to double the number of transistors every 2 years, right? Why we're able to do so? Because technology advances, the manufacturing of the chips or the wafers. So we're able to put more transistors in the same square area, basically, right? And this is called the technology. When we say 1 nanometer, that's simply, do you know what is, when we say technology is 7 nanometer or 9 nanometer, what does it really mean? The size of transistor is a closer answer, but there is a more fine-grained one. When we say the size of transistor, what is exactly this? Because nanometer is not really a unit of size, right? It's a unit of length, right? Yeah. Yes, exactly. So that's basically the width of the transistor gate, right? So that's which can be a reflection of the transistor size, which is a reflection of how many transistors you can put in a square area, right? So the lower that goes, the more transistors you can put in the same area, which means you have more capability, right? This is what we mean by technology. And VLSI courses and electronics, in some sense, are mainly covering this, as we said in lecture 0. Now, going back to what we care about, would technology impact instruction count? Yeah, this is a little bit further, right? Again, someone can say, okay, technology impacts processor organization, impacts ISA, and then, well, but that's a little bit far, right? So I would say, yeah, mostly no here, right? You all agree, or there's someone that has a counter argument? Good. So now we go to the second term, CPI, cycles per instruction. Algorithm. I guess Steven said yes. Maybe, yeah. So there is the side of the debate of saying, well, maybe there is some argument there. Is there someone saying no? It does not impact cycles per instruction. It doesn't really matter whether I say yes or no, but as far as you have some sort of an argument, a reasonable argument, yeah. Great. Yeah, on average. That's in fact an excellent point that I guess puts you on the same side of the debate with Stephen, right? Like you're saying, yes, it impacts, but I guess you're saying it in a different way. You're saying in the reality, CPI here is the CPI average, right? And CPI average, as we have done in the problem in the Friday lecture, is we look into the types of the instructions I'm executing. In our example, we had int, floating point, or branching, and memory load store. So one algorithm, for example, can try to minimize a certain type of instructions that are known to take longer to execute, memory, for example. And for that reason, I improve the overall CPI. Well, that's a very compelling argument to me, right? possible. You are not now focusing on one instruction, one type, but the overall average of the program, which is definitely a function of the algorithm, right? This makes sense? Good. So I'm more convinced to say yes here. When I put X means, yeah, there is an impact, right? There's a relationship in this matrix, right? What about programming languages? Yeah. Yeah, yeah. If we argue that algorithms impact CPI, which is a higher level in the software stack layer, then I guess this takes us forward that simply, well, programming languages are just saying, well, how do they implement these? This certain line of code in that language is translated to what type of instruction, and on the other hand, compiler as well, right? So there is also some, if this is yes, then this is yes, right? But I will put this in a box here. Good. What about ISA? Clearly, right? ISAs is, I guess, now start becoming more clear. As we said at the beginning, some governing rules is that if I'm talking about an instruction count, you are more inclined to say that the software layer impacts you more because it's more related to the software. CPI and clock cycles, they are more inclined to say hardware really impacts you more. But I guess what I'm looking for is that, can you give me an example that ISA is really impacting your average CPI? Yeah. Great. So can you elaborate a little bit more?
Oh, yeah.
True, true. An excellent point. So basically, a RISC, like the MIPS instruction set, it's the one that is simple, every single instruction. And today's lecture, hopefully, or tomorrow's lecture, depending on the time, we're going to cover this in more detail. This is simply that the RISC instruction set has a very simple philosophy. Every single instruction only does one operation at a time, right? And we had the example, if you want to swap two variables last time, again, in Intel, I can do it in one instruction. They have like 3 memory operands, for example, or 2. But then in MIPS, I need first to do a memory load operation, and then I simply then do the swapping of registers and then do a store back, right? So now that means one instruction in MIPS, because it's only doing one operation, definitely its CPI is going to be less, right? While in x86 or CISC instructions, for CISC instruction set, the only existing winning instruction set at the moment is in fact the x86, right? While everyone else is a RISC instructions. And I don't want to delve into that discussion in detail because we are going to have it likely tomorrow. But the main idea we are looking for here is because in CISC, one instruction does a lot of job, it takes a lot of time to execute, right? While for RISC, it's only doing one operation at a time, which means the CPI of one instruction is faster. Someone can say, but I have longer number of instructions, right? But this does not impact CPI. It impacts what? Instruction count, right? So you have the impact on another side. So usually CISC is better in instruction count, but RISC is way better in CPI. Okay, good. So this is a clear one. What about processor organization? That's simple, right? How do you design your processor? Well, it's going to define really how many cycles you take for your instruction, right? So that's clear. What about technology? Yeah, when we say cycles, we are mainly talking about architecture level layer, right? So cycle is not really saying, okay, how many transistors I take there and how fast in real time I run. I'm talking about cycles, which is the time unit at the organization level, right? How fast is that cycle? Well, that's a different story. How fast is the cycle is not part of CPI. It's part of what? Clock cycle or frequency or bit, right? So technology here, again, I would have a question mark. Likely not. Good. Are we good? And by the way, just to throw in a stone in the lake, well, someone can say, but if I have a better technology, I have more transistors, I can implement the organization better, which means my CPI can improve, right? But yes, that's an implicit indirect impact, and this is why it's a question mark. Let's focus first on the direct impacts, right? The things that are talking about that layer. Clock cycle, algorithm. Is there anyone that's saying yes, the algorithm would impact the frequency of the machine? Yeah, well, that's a very, very interesting point because someone, and to be honest, I didn't expect that someone like raises this point, but there is something that is right now in modern processors that says dynamic frequency scaling, right? But this is not what we're talking about. Dynamic frequency scaling, you have the ability in the software to basically like run at different frequencies based on, do you want really to consume more power, but then you really run a higher frequency, you get better performance, right? An example, a very simple example of this, although it's in fact not dynamic, only static, is the modes you have in your laptop or in your machine where you're plugged in or running in a battery. You're able to choose performance mode or power saving mode and these type of modes, right? But that's mainly static, not dynamic. But let's put this aside. Let's say the software is not able to control that, because even in this one, you are not really impacting how fast the machine runs. You are picking among previously defined options, right? For example, and I tell you, you have these, we call them in hardware frequency taps. So you have frequency 1, frequency 2, frequency 3, and then you choose among them based on what you want to do. So you don't define the value of F1, F2, F3, but you're choosing which one to use out of them, right? So the software is in fact not impacting the frequency, right? That's clearly. Programming language, not as well, right? Compiler, I would also say not as well. What about ISA? Yeah. Well, not necessarily. AMD and Intel both are x86, right? ARM and others are mainly RISC ISAs. Well, they have different instruction sets, but they don't define your, like, whether you have a certain type of instruction or not does not define really your frequency, right? And the main reason for this, as we're going to cover in detail for the pipelining and out further execution, is regardless of the instruction, you are able to break down into well-defined stages, right? So having a certain instruction or not having it should not impact really the actual running frequency. Processor organization. How do whether I put in a function unit or not? Again, what do you mean by processor organization? You have multiple types of function units, ALUs, floating point accelerators, load store units, and then how do you connect them together, register files, and how you connect them? Does this impact how fast you can run your machine? Yeah. Yeah. Is there anyone saying no? Does not? What do you think? Well, it does, clearly, right? Maybe now it's not very clear in your mind. After we finish the pipelining series of lectures, you'll see clearly that it impacts your frequency. How do you architect your machine? It defines how many operations, how much effort you do in a single cycle. And if you are not able to finish within a certain cycle, you have to increase either add a pipeline stage or increase your clock frequency, right? So, and this, I guess, is also something you can more or less make a conclusion about from 3DQ, right? How do you design your RTL simply determines how fast you can run, which is what we call the critical path Fmax, right? This is what defines your clock speed, right? So hardware design, RTL computer organization clearly defines your frequency, right? Your running frequency. Technology, yeah, for sure, right? That's really the clearest part, because in technology, well, I give you more resources so you can run faster, right? And again, the clear rationale here is by Moore's law, we were able to, because we didn't really hit the Powerwall yet, in late 90s and early 2000s, we were able to double the frequency every couple of years. In reality, there weren't a lot of architecture innovations back then. All the gain was coming mainly from the clock frequency, right? It was a very simple job, right, for Intel and architects, right? Because I can optimizing something here and there, but as far as I double the frequency, you get double the performance. Okay? Great. So are we good in that discussion? A big disclaimer here is if I flip in the slide and start looking into the answers, you might find different answers. Does it mean that this is wrong or the other one is wrong? No. It means that simply there are different rationales. Again, we answered the clear ones and we left a gray area, and you will find in the answer table that there are some clear X's and there are like shaded X's or a little bit more transparent X's, and also again because of that impact discussion, right? Good. Adding one X at a time. Good. I'll leave it for you to look for. And again, this is very, very important conceptually. So try to comprehend it as much as you can. Take every single cell, think about it. And if you got confused why that's the case, I would rather even sit down and try to write the reasoning, right, of why that's the case. And if you got questions, come and talk to me, right? Good. And then also we discussed last lecture Amdahl's law, and in today's tutorial, which is after this lecture, Ali, the TA, will go with you through solving from the first problem set, which I already added in Avenue. You will find that there are some practice questions for performance, and we're going to solve these problems in the tutorial, okay? Because we already finished the performance, so we'll dedicate the tutorial for solving problems related to this. Good.